Hello, everyone. Nice to see you here. Thank you for being on time. Uh, so we're just going to wait until like everyone is here. You can, say a little bit about yourself in the chat. Say where you're from, which city you're from, what country you're from.
Hey, hello. This is me, Tico from Tbilisi, Georgia. Working at Ilia State University currently, and happy to be here on our first session of Codeacademy.
Yes, thank you, Tico. So, welcome to the first speaker session of Codeacademy's Tbilisi AI and Machine Learning chapter. I'm Negar, the organizer of this chapter, and I'm a junior machine learning engineer. And this is my third year studying computer engineering in Ilia State University. Speaking of Ilia State University, they're my partner for this session. And I'm very happy about it. It's really nice. And you just heard Tico say a little bit about herself. And yeah, she has helped me immensely with organizing this event. Thank you. So, wow, we have 11 people here. Amazing. And you can turn on your cameras if you want. We would love to see your faces. But just be informed that we're recording this event. So, and it's going to be uploaded on YouTube. So if you have a problem with that, then maybe don't, but we would love to see your faces. We're just going to wait maybe like 2 more minutes, and then we're going to officially start.
Negar, before we are waiting, allow me to fill the silence with this good news from from Ilia State University. I will use this time to say that we have lots of programs for both students and high school students as well. For example, together with Negar, we are doing Python programming courses. Yeah, we are many more courses coming up, such as engineering school for school girls, where girls are studying drones and also making their own robots. So many exciting things are happening at Ilia State University, and happy to help. If you have any questions, just contact me at any time. I'll share my contact information in the chat box.
And thank you, Tico. Just one more thing. If you want to like keep in touch with us, we're gonna have a lot of events like boot camps and just speaker sessions and coding sessions and stuff like that. Make sure to join our Discord. The link is like in the chat right now, so you can join. And yeah, there's a lot of people actually in there, so there's a lot of networking happening as well. Okay, so about this session. This is my actual like first speaker session in Codeacademy, and I'm very excited about it. Our speaker is Camille von Hoffelen. He was actually like my professor last year, and like he's the reason that I became a machine learning engineer. So yes, Camille, take the wheel.
Hey everyone. All right, should I share my screen, perhaps?
Of course.
Can everyone see this?
Yes.
Oh, I'm at the end, wait, that's not good. Oh, no. There you go. All right, so thanks for having me, Nagar, and everyone else. My name is Camille van Hoffelen. I'm a machine learning engineer and CTO now as well at a company called Watergenics based in Berlin. I've been a machine learning engineer for like almost 7 years now. And my thing is to get, you know, big models working on big production systems. So I thought I could focus a bit on that side of machine learning for once, perhaps. And talk about model serving and model deployment. Now, those are huge topics, usually solved by big engineering teams, and I'm only, perhaps for the best, going to talk about half an hour today. So take this maybe more as a primer for the basic concepts of you know, the things to worry about if ever you wanted to get a model serving and deployment system in place. So let's get started. I see predict as the final frontier, right? Because typically when we're experimenting with machine learning and doing data science, that's kind of where we stop, right? If it works, the predict works, then it's all good. So let's take an example. We have Felix here, our favorite data scientist. Felix is a very talented data scientist and has built the world's best fruit classifier. So this is a deep learning model. It is awesome. It has 99.9999% accuracy. And that means, of course, that when we feed it an unknown fruit, it can tell us when we call the predict method on this model, it can predict very accurately what type of fruit this is. And that's all good, right? But now Felix wants to share this model with the world, right? Maybe Felix starts a new company that specializes in fruit classification. Maybe Felix gets a job in an awesome fruit company or whatever. But the basic question is, how does Felix call this predict function, right? Which is what we want the model to do, but outside of his Jupyter notebook, where of course he has done all this experimentation. So that's what we're going to talk about today. The first part of how to call predict outside of Jupyter notebook is called machine learning and model serving, right? So let's there's several paradigms in model serving. We'll start with the simplest one, which is a monolith architecture. So take Felix. When Felix wants to run typically code somewhere else, there's a very simple technique, right? Felix just copy paste a bunch of code and it's probably going to work, right? So what we could do is, if you have an existing software stack, if you have an existing application, you could just copy paste in there, load a model file, call predict on whatever's coming in, you know, as part of the actual software, and do more stuff with whatever the result is. Maybe display it to users, maybe use it for further analysis, right? And this of course would have to come with some kind of model file resource that you stick in there somewhere in a folder. And this is okay, right? This works. This is now officially outside of your Jupyter notebook, but as you can probably guess, it's fairly limited. So what's the problems with just copy pasting and sticking your machine learning code somewhere? Well, first of all, it is probably going to be slow, right? We know neural networks are not the fastest thing in the world, and you're going to end up blocking whatever code was running in the first place. And sometimes that's okay, but sometimes that's very problematic to have your entire software stop for a few seconds. It's also not going to run on the best hardware, right? Either you're running your prediction on regular hardware that's probably not even a lot of memory, or you're trying to fit regular software into GPUs or whatever, which doesn't sound very optimal. You're going to be heavily loading big resources, right? Those model files are can be really large, and having this as part of the software can make it even more slow and even more memory intense. You can have language conflicts. I mean, I don't know if any of you have tried to write machine learning code in Java or in C++. Is kind of okay, but it's, you know, depending on your stack, this is maybe not the best way. And often data scientists like to keep around playing with Python because that's where all the nice libraries are. So possibly some language conflicts, but then most importantly, this does not scale, right? The moment you want to predict more or faster or more stuff, you're stuck because you have those lines of code, and unless you're going deep into parallel processing or whatever, it's not a good idea, right? So this is clearly not a great list, and thankfully we'll get to other approaches. But the conclusion around monolith architecture is it can work sometimes. There are some use cases where it's okay, but it's kind of hacky and it's very limited. So to understand how to move forward from monolith architecture, we need to understand a bit more about regular software architecture. And whilst I'm not going to do an entire presentation on this, because that's also a vast subject, just a little bit of a primer on what microservices are and how it basically works. So when you have regular software or modern software, let's say, let's take a fruit factory type theme here, right? So you have fruit coming in, which is going to be your data, whatever that is. And typically you don't just feed that to an app and then, you know, it just displays the result out. You'll have different components, and these components are called services, and they're usually separated by basic function, right? So maybe we'll have an inspection service whose role is to inspect these fruit. And depending on if the fruit looks good or not, maybe it'll pass it on to a washing service, right? That'll clean the fruit nicely so that it can be then forwarded to the user or the customer or the person who's going to eat the fruit. Now, when I say forward, these services in a microservice architecture are independent. They're different pieces of code, and they're communicating through either APIs or message queues or remote calls or something. But this is not the same piece of code. This is different from like having classes or having functions. This is, you know, independent pieces of software communicating synchronously or asynchronously. And this is really important because that's kind of the definition of a microservice architecture. It is loosely coupled. That allows us to get more complex. So if we take this example further, we could also have a compost service that if the inspection is bad of the fruit, maybe it's forwarded there. And gradually, you know, more and more complex software, you're not adding lines to your code, but you're adding new functions, new services, right? That are all talking to each other using these methods. Anyways, so that's your application overall. And it's made of several distinct services. Now, Felix was listening to all this. And Felix figured out, okay, that's a good idea. If I don't want to copy paste my code somewhere random, right? Maybe I should make my own fruit classification service, right? And maybe whatever other pieces of code, whenever they need to know what fruit this is, maybe they just call this service. It can be as simple as a REST API, right? So it'll be like, get me or put the data and get the information back. Thank you, this is an apple, and maybe then, you know, the rest of the software moves on. This, you know, model microservice could be very simple because it only does one thing, right? It has the data in, that you usually feed to your predict, and then it pushes back the rest of the data. And then it can be bundled with whatever model file, whatever that is, a sklearn pickle, a PyTorch file, a TensorFlow, whatever, right? And then it's loosely coupled to the rest of the system. So we cut a lot of the issues that we had previously. So that would be an example of a model endpoint or a model microservice whose sole purpose is like, I have this model, give me the data in, and I feed it back. You can also have a slightly more complex architecture for model serving. So sometimes let's say the data input's a bit different, or it's changed. Now it's not just fruit, but now it's all types of food, right? And let's say that our classification service, well, it requires more than one model now. It needs a fruit classification model, but it also needs a meat classification model and a vegetable classification model. Well, we could keep the previous architecture where we have one microservice per model, right? Very simple. Or we can also have a more general function, right? So this microservice now has a bunch of models in the back, and it's able to maybe pick the right ones, right? Or just give back all the information. But the idea is similar. When you're when embedding machine learning in a microservice architecture, you typically want to keep this separate from the rest. And here are the advantages. First of all, you can have asynchronous calls between those services, meaning that when you're running your very slow neural network, you don't have to block the rest of the software. You can use specialized hardware very easily, right? This single service can run on GPUs and not bother the rest. Your resource loading can be more efficient because all of a sudden, especially when you're dealing with one model, maybe it can stay in memory and you don't have to play with that all the time. You can have a polyglot architecture without too much effort, meaning you can keep running Python and it can still talk to the rest using a REST API, right? And finally, and most importantly, it's easy to scale, meaning if, 2 months later, your requirements on how fast your predictions have to happen are tenfold, well, you can just scale up and have like 10 servers run in parallel, or you can triple up the memory without affecting the rest of the services. So microservice architecture, clearly pretty good idea. It is more elaborate than just copy pasting. You have to take care of the communications, of the actual DevOps of the servers, run the hardware, but it's more flexible. So for proper usage, it's definitely the way to go. All right, so we've seen 3 model serving paradigms. Globally speaking, monolith, inject your code somewhere. A model microservice where you have one microservice per model resource, very simple but effective. And a more generic prediction microservice, which is a bit more controllable, but maybe a bit more complex. Now, you might think, okay, that's it, right? Like, I get it. You don't want to use predict in your DrewPython notebook. We've now learned how to include this in a modern software stack. Are we done? Well, unfortunately not, because machine learning code is a bit weirder than regular code. So if we just did this, we would still have issues. And how to deal with these other issues is called model deployment. So let's look a little bit into our fruit factory example, right? So we now have all these microservices. They all work beautifully together. They're talking to each other. They're not affecting each other. Felix is very happy. If we look a little bit more into our fruit classification service, well, here's a problem. You see, this code is not experimental code. This was not directly taken out of your DrewPython notebook. This is probably more optimized prediction code. And so straight away, one can wonder, well, okay, where did this code come from? Did I code this twice? Did I first mess around my DrewPython notebook and then rewrite everything for my microservice? Well, this is called dev prod parity, or sometimes it's the experiment to production gap. And it's a problem. This is one of the 12-factor app principles, if ever you're familiar with that. You need your development environments and your production environments to be as close as possible, or bad things are going to happen, right? If you have to modify them throughout the way, mistakes are going to happen and you're going to end up with a wrong thing in production. And machine learning is particularly tricky because naturally there's a big gap between dev and production code. One example of this is training code, right? When I'm experimenting, I need to train the model, but often in production, I don't need to train the model. So this is like weird dev code that is still very important, but I don't have to like actual deploy it, right? One example of this gap. Another example is, in data science, we like Jupyter spaghetti code. Like that's our jam, you know, that's how we thrive, is being able to try little things, seeing graphs, whatever. And that's all good, but that's not optimized production ready code. So there's always going to be a bit of a jump there. And the aim is to minimize it. So the question is, how do we minimize the effort, the time, and the steps between me fiddling around with experiments and actually having like production ready microservices? Well, there's a few main avenues down there. This is a bit of a broad topic, but hopefully this gives you a bit of an idea. So the first idea is to productionize your experiments more. So when you are fiddling with your Jupyter notebooks, there are ways of making this a bit more legitimate. First of all, by standardizing the prediction code, right? For example, by having a generic interface when you're predicting stuff with your models, no matter what's in the back, if it's a TensorFlow, PyTorch, or whatever. That helps a lot, right? Because then that just falls into the same template. Standardization of model binaries can be helpful with this. I don't know if you're aware of formats like ONNX, ONIX, but those are ways of representing models no matter the framework that built it. Also one step closer to something a bit standard and production ready. Encapsulation is always your friend. You know, not always fun when experimenting fast, but at the end of the day, if it's I don't know, like a data pre-processing that happens 1,000 times in your code, perhaps take this, put it in the library, reuse it in your experiments. That way, that library code is a bit more legitimate. Maybe it's actually got unit tests, and maybe you can actually use it in production. And of course, then code quality. You know, there's a lot of tricks you can do to keep up code quality without compromising on speed. Stuff like pre-commit hooks are awesome and very easy and will immediately improve your code quality even when it's experimental code. The other big avenue is to experiment directly on production code. So when we have those microservices, if they're done well, you know, it's still data in, prediction out. So we should be able to take that and feed it data sets and evaluate the results, right? One thing that helps a lot with that is containerization. So using Docker and things like this make it even more standardized as a microservice and even more testable in various QA environments or whatever to try to probe the behavior of the final microservice and check that it actually does what it did back in your Jupyter notebook. In order to do this, though, you need a really good data engineering and data storage, right? If your data set is a random CSV file on a computer somewhere, that's going to be really hard to test your microservices efficiently. So proper, highly available version data sets, probably in a data lake, is also the way to go. And if you can have that accessed at any time from experiment to production, that really makes your life much easier. And finally, to glue all of this together, super important to have automation, right? Automation on all the stuff you don't want to have to worry about, like dependency management, like packaging all of the classes and all of the binaries together in a nice, you know, either a nice package or directly into a Docker container, right? Integration testing should be also automated. From the moment that we have Dockers running prediction microservices, we can test all of this automatically. And then, of course, just general CI/CD pipelines that do all of this in a testable, verifiable way from start to finish. All right, so that was a bit of a mouthful, but this is, you know, a major problem when we're talking about deployments. How am I doing on time? I'm doing not so well on time, but okay. I'll speed up a little bit. Okay, so here's now we've talked about the issues with the gap between experiment and production for this code. But let's assume that we fixed all of this. We have awesome automated pipelines for our code. There's still another problem. These big model files, they don't fit in Git. And that sounds like a very silly problem, but it's a big problem. So, you know, they can be easily like 700 megabytes or several gigabytes in size, and Git first of all, doesn't support or these kind of sizes, but also is really not made for that. You don't want to have to download. Imagine every time you edit your model, you have to re-download previous versions of that copy. It's a nightmare. Don't do that. But here's a problem. We want to version models as well. I mean, version control for code is literally the staple of modern CI/CD pipelines and DevOps for a reason. It's because managing changes in your code is crucial if you're going to have easy software deployment. So we still need versioning for our models. The problem is they don't fit in Git. Also, they're coupled to prediction code, right? This code there. These are coupled together. Sometimes I can change the model without changing that, but sometimes I change the model, I got to change that, like maybe some pre-processing or some tensor sizes or whatever, right? So these things are coupled, and unfortunately it's coupled to something in Git that is versioned separately. So that's a possible headache. But also models depend on a lot more things. Regular code just depends on itself. Models depend on training code that created the binary. It depends on the data that was used to train the binary, right? So you have all these hidden dependencies that we have to model somehow. And the cherry on the cake is that actually models also have an independent lifecycle compared to the code that runs the predictions. And what I mean by that is models becomes obsolete even when code doesn't. So if your fruit classification service was state-of-the-art, world-leading in performance in 2019, well, maybe it turns out that in 2021, people started eating a lot more oranges, and that completely messes up the accuracy of your model, and your model is now obsolete. This is something normal. This isn't like a failure as a data scientist. Models have life cycles, and they need to be recycled and updated, sometimes separately than the code. So all of these things together is a big headache. And the question is, how do we track and manage these model changes, not in Git? Well, again, a few avenues here, a few pointers to what a good system should be able to do. First of all, the concept of a model registry. So a model registry is a central repository for model binaries. Like we have a central repository for code, which is Git, you have the same thing for all of your model files and all of your packages. It should support metadata, both for searching, because ideally you end up with a lot of different models and it's going to be a headache remembering where they are, but also for lineage. So understanding an example of an essential metadata on the model is what data set was used to create it, what training code commit was used to train it, right? So all of this needs to be metadata so you can actually track all the inputs and the dependencies. It needs to support, it needs to make these models reproducible. So this is through metadata, right? So if the model disappeared out of the registry somehow, right, your S3 bucket is deleted, you should be just with the metadata able to reproduce all of this from scratch, from the data and from a commit and everything else. And finally, a model registry should support lifecycle management. So again, because models have a bit of a lifetime, you should be able to track this. Typically, this happens by having different stages, right? So you might have like dev, staging, and then prod, and then have some monitoring on it. But all of this is often literally a UI, just to have a bit of sanity when you have 30 models in production and you want to keep track of what's going on with which. Other essential avenue here, good data governance. If you don't have data governance, your models are going to be a mess, right? It's all upstream. So knowing what data was used where is essential to understand what model is going to do where. This also happens with versioning of data, because every so often your data sets will be updated. You'll move, maybe even you'll just extend it. Well, if you think that's a cascade straight away, right? If this was a data set used in production, if you extend your data set, you need to retrain your model. Your model needs to be updated, needs to be redeployed to production. I mean, it's an entire cascade of dependencies. And of course, lifecycle management for data sets as well. And finally, again, the glue that puts all this together is automation always. You want to integrate all of this into experimental workflows so you don't have to worry about it when you're running Jupyter. Ideally, you're in Jupyter pressing buttons and training models, and those are directly saved in the model registry with lots of useful metadata. So you're not doing anything manually, right? Integration testing again, and CI/CD again. You can see the pattern here, right? Which is all of this automation gluing together the versioning and the gap between production and experiments. All right, so let's finish here by going back through our first example. So remember how we asked, okay, we got this awesome model, but how do I actually call predict on this thing outside of my notebook? Well, let's go through what a modern system could look like. So let's say that we have, well, the first step is don't use the model copy paste, actually make a microservice for this model. There might be here the fruit classification microservice. As we talked about earlier, you get these fruits coming in, these fruit data, and you get classifications coming out. But now to illustrate what a good model serving and deployment, like the value it takes, let's take a use case where we need to change this model, right? So Felix realizes, like, actually, I've got this way better data set that's like twice the size of the previous one. So now I want to update that. And that's going to affect the chain of dependencies, right? So if Felix has set up a nice system, this trained data set is put directly into a data lake. It is version data sets. So the data lake can keep track. Oh, this is the same data set as before, just V2. This is now really easy for Felix to do experiments. Maybe check, oh, maybe I try a deeper model with this. Maybe I try a different set of hyperparameters. All of this is automatically pushed to the model registry. So all these binaries and all this nice code packaged together is kind of ready to go. And then whenever Felix is confident that the experiments are good enough and wants to update the actual microservice, it's one click of a button. I want this from experiment to production. All these CI and CD pipelines kick off. You have, you know, it's put into staging. You have QA stuff going on. You have integration testing, all the good stuff. And it eventually updates in a continuous way the previous microservice to have better, in fact, perhaps the best fruit classification service ever. All right, so key components of a system like this. It needs to be reproducible. It needs to be audited, so you know these manual steps as they happen. Automation is, of course, key. And really the key word here is scalability. Why bother with all of this is that this allows to scale on every single step way easier. And scaling should always be an issue if things go well in a startup, in a project, in whatever. All right, so summary. Model serving is the art of actually executing machine learning code in production. We've seen a few paradigms to do so. Model deployment is the journey, is how do I get all my stuff in there actually predicting, right? And if you want an important keyword here, this whole field, right? This whole journey of product making machine learning code into products is under the field of ML ops, which is the DevOps equivalent. But as you've seen, there's quite a lot of ML special sauce going into this. So ML ops is this field. And pro tip, it's 2021, machine learning is not new. Maybe 10 years ago, you had to build a lot of this yourself, but nowadays there's frameworks for almost everything. So I have a lot of logos here. Things to keep in mind, some of them will be open source, some of them will be paying, some of them will be open core. You know, some of them will be for more academic experimental things. Some of them will be for like huge systems on Kubernetes only. So whenever picking a framework, you know, do your research. Keep in mind that there's no better one. There's just one for each use case. And this in the middle is a great list. My go-to reference, by the way, on any ML ops related framework. So please check that out and go through all of the awesome stuff out there. And that's it. please ask me any questions. I've added my details here as well if you have some questions later. If you can't sleep at night because you're thinking of model serving, feel free. And yeah, hope it was interesting.
Thank you so much, Camille. Nice to see Felix again. Yeah, so that was a really interesting topic, actually. Like, my brain is buzzing still, but yeah. So, guys, now it's Q&A time. So if you have any questions, you can raise your hand, like by the reactions that Zoom has, and then you can ask your questions from Camille. If you have any, that is. Yes, Ahmed.
Sorry, I put a reaction of claps, but no worries. I had a question related to at the end of the presentation. It said that many model registries they needed like Jupyter and Git is not so effective or efficient for it. So the options that you gave at the end of the slides, were they the options that we have to do this model training and data sets with huge sizes, like you said, 700 gigabytes or something?
Is your question asking if the model registries can also help with the training?
Yeah, and are there any examples, like popular examples, where we can train these model registries other than like Jupyter and maybe save our data sets in like Git? Are there any other options or examples that we have?
Okay, yes. Okay, so maybe two parts to the question. Okay, so just to be clear, the model registry is just a place. You can think of it as a model database, really. It's just a place where you put your trained models coming from anywhere, ideally. So you have options, because my experience working in big companies is you'll have some people that want to work on local Jupyter notebooks, and some people that want to work on like super distributed, massive AWS clusters. And you got to make everyone happy. And the idea of a centralized repository is that it doesn't matter where the binaries come from. They should go in the same place. They should have the same amount of metadata, and they should integrate to the rest of the system in the same way. So, but to go back maybe to your question on model registries also taking care of some of the training, this is kind of why I didn't get more into frameworks, because it's a bit of a mess. So MLOps is more legitimate than 10 years ago, but it's still a little bit in its infancy. So all of these logos, and all the other logos you'll find on this list, it's not as if there's one model serving, one model deployment, one model registry, and one model training. A lot of them do a bit of both, a bit of three things, take a bit over each other. And so there's no better way. Honestly, you just have to check them out. Hopefully this presentation at least gives you pointers on like, oh, I know what that means. Like, I know what that is. If a framework tells you that it does model serving, that should be, okay, so it's worrying about the actual execution code that will be running, right? So a lot of this will also take care of some of the training, as you pointed out. So yes, some of them do kind of like everything. I'd be a little bit cautious of those, because there's usually a cost for that. If it can do everything beautifully, usually it's either less flexible, or you have less control, or maybe they want you to pay a lot. So yeah, I don't have like a one only answer, but some of them will do more than others, and you kind of have to explore yourself.
Yeah, thanks. That answers my question.
Actually, I have a question for you. This is not related to the lecture that you just had, but just like top of your head, like where do you think someone that wants to start machine learning, like where to start, basically?
Like from scratch, from nothing.
Like imagine, yeah, like Python a little bit, but like you want to get into machine learning.
Well, thanks for asking, Nigar. I made a course that somewhat corresponds to these requirements, so you're free to check it out as well. It's on my GitHub and open to the world. There's also a lot of other courses, to be quite frank, in machine learning. I'd say that most of them focus on how to get from basic Python to like running a Kaggle competition, but there's still a bit of a missing link on this kind of stuff, right? Like, how do I actually engineer this in production? So keep an eye out for those kind of resources as well.
Thank you. Jay, please ask.
Hi. Can you post a link to your GitHub to your course in the chat?
Absolutely.
Okay, cool. Thank you. Because that was an excellent question.
Actually, we will be linking the slides to this session in our Discord server as well.
Cool. Maybe I'll just add it to the end of the slides then.
Yes, that's great. Any more questions, guys? Okay, I assume not. Thank you so much, Camille, for being here. It was a really good presentation. Thank you.
Cheers. It was a pleasure.
Yes, thank you. Okay, so one last thing is that my next coding session is in 10 days. I've called it Python Essentials. So if you know Python, but like you're a little bit rusty and then like you haven't done it in a while, and maybe you just know a little bit, but like you forgot most of it, this is for you definitely. So we're just gonna go through all the essentials that you might need. And the follow-up session of this Python Essentials will be working on NumPy and Pandas libraries, which are like the core of machine learning. And yes, make sure to join our Discord so you can RSVP for our events. Tico, any last words?
Thank you and congratulations. Looking forward to other meetings.
Okay, so thank you all. Thank you, Camille.
Bye.
Thank you all, and see you on Discord. Bye.
Okay, goodbye.
Goodbye.